Hello, everybody. All right, so this week we are focusing on functions. We're continuing our work on functions. We're going to be focusing specifically on linear functions and proportional relationships. So if you have your notes from last week, this would be a good time to get them out. Or if you haven't watched last week's lesson, this would be a good time to go back and find the link to last week's lesson on our Google Classroom, because you'll need to watch that first before you watch this lesson. All right, so our learning goals for this week. By the end of this week, you will be able to identify linear functions, identify rate of change or slope of a relationship when represented in multiple ways, including on a graph, an equation, or a table. So last week we talked about the different ways to represent a function. Right? We talked about describing them with words, representing them with graphs visually, using tables, so like a list of numbers in a table, or an equation, so an algebraic representation. So we're going to be continuing our work with those multiple representations this week. And then finally, our last goal is to compare two different proportional relationships represented in different ways. For example, you might be asked to compare a distance time graph to a distance time equation to figure out which of two objects has a greater speed. All right, so along with your notes from last week, you're definitely gonna want pen and pencil, pencil and paper, or pen, whatever you prefer, and your GED math formula sheet. You might want a calculator. You won't necessarily need one, but you can have one if you'd like. When I ask questions throughout the video, I really recommend that you pause the video and give yourself a minute to think about the question, try and write down an answer before you start playing the video again. All right, so first question I'm gonna ask is, I'd like you to think back to last week, think back to your previous learning experiences in math, and try and remember, what is a function? What's the definition of a function? Well, a function is a relation between input and output where there's exactly one output for each input. So broadly speaking, a function is this relationship between two things, between input and output, and it's a specific type of relationship where there's exactly one output for each input. And I've got a couple of examples here. So this table should look familiar to you if you were on the lesson for last week. So we've got this table showing input for a function and then the resulting output. So for this specific function, when you put 0 in, you get 0 out. You put 1 in, you get 15 out. Put 2 in, you get 30 out. 3 in, you get 40 out. 4 in, you get 60 out. So notice here that for each of these inputs, there is only one output. Right? So 1 only goes with 15. 1 doesn't go with any other number. 2 only goes with 30. Doesn't go with any other number. 3 only goes with 45. Doesn't go with any other number. Right? So that's that special input-output relationship. And then here on the right side, we've got another example of a function. Again, something that should look familiar to you if you were on the lesson last week. So this is a visual representation of this same function that's shown in the table. Again, this graph, it's linear, so this is a linear function, it's a straight line, and it passes the vertical line test. That's how we know that this is a function, that it has that special input-output relationship. If you don't remember what the vertical line test is, you're going to want to go back to last week's lesson to remind yourself about it. All right, so we're going to be focusing specifically on linear functions this week. So a linear function is a function that has a constant rate of change or slope. Ways that we identify a linear function. Well, one way we can identify it is with that constant rate of change. We're going to talk about that a little bit more later. We know it's a function if it's a straight line. We know it's a linear function if it's a straight line when we graph it. So if it makes a straight line when graphed. And then if we're looking at an equation, then we know it's not a linear function. It's not a linear function if we see exponents or roots on the variables, or if we see that the input variable is in the denominator of a fraction. So those are characteristics of things that are not linear functions. And you can see my cat Jemima in the background there. Hey, Jemima. She's very sad that she's not outside with me right now. All right, so let me give you an example of what I'm talking about with respect to those equations. So examples of equations that are not linear. Not linear. So if we have something that looks like this, y equals x squared. So I look at this equation and I know right away, that's not a linear equation because my input variable, x, has an exponent, right? It's x to the power of 2 or x squared. So I know that that is not a linear equation. It is nonlinear. Or if I had something like this, y equals 3 over x. So there, again, my input variable is in the denominator of a fraction. So this would be nonlinear. Examples of what a linear equation looks like. Again, we're going to see a lot more examples later on in the lesson. But basically, in a linear equation or a linear function, your variables just don't have anything extra going on with them. So let me find my cursor here. There we go. So a linear function, a linear equation, it's going to look something like this. So y equals 4x. That's a linear function. Y equals 1/2 x plus 7. Okay, so in both of those equations, the input variable x and the output variable y, just regular old variables. There's no exponents on them. There's no roots on them. They're not sitting in the denominator of a fraction. Just kind of nice regular variables. So that's something to look out for when you're trying to identify linear functions. Okay, so we mentioned this characteristic of constant rate of change or slope. Now this is something you may have worked on before. Slope is a really important concept when we get into functions and graphs and equations. It's something that will come up a lot, so we're going to work on it a bit today. But the basic definition of slope is, you can also think of it as rate of change. And what it is it's the ratio of the change in y to the change in x. So this word ratio, if you remember what this word ratio means comparison, right? Comparing two things. So slope is a comparison of the change in the vertical direction, so the change in y, to the change in x, so the change in the horizontal direction. So we're comparing change in y to change in x. And again, we're going to see lots more examples of that later on in the lesson. So last thing to talk about on this page, why do we care about linear functions? Well, we care about them because they're on the GED test, right? We're trying to pass that test. But we also care about linear functions just because they are very, I keep losing my cursor here today. They are very common. Very common. So, right, we as human beings, we like to see connections between things. Our brains just kind of naturally draw connections, see relationships between things. And so this idea that we have of the relationship between input and output, that's something that comes up a lot. And these linear functions also are something that comes up a lot. So anytime that you're talking about like the amount of money that you earn based on the time that you work, right? So if you're an hourly worker, that's a linear function. If we're comparing distance and time to average speed, that's a linear relationship there. So it comes up a lot, and we're going to see some examples of linear functions again later on in the lesson. But we're interested in them really for two reasons. One, because they show up on the test and we want to do well on the test. And two, because it's just a very common type of relationship. Okay, so on this page here, we've got some examples of linear functions and nonlinear functions. So over on the left-hand side, these are all linear functions on the left-hand side of the screen. So when I look at the first equation here, I know this is a linear function because, and it doesn't have any of that crazy stuff going on with the variables, right? I don't see any exponents or roots on the variables, and none of the variables are down in the denominator of the fraction. That input variable x is not in the denominator of a fraction, so I know that's a linear equation. The second equation here, again, is very similar. So we have this function notation, f of x, but if you remember from last week, f of x means the same thing as y, it just means your output variable. So f of x equals 1.5x minus 7. So again, nothing crazy going on with our input and output variable here. I don't see any exponents or roots on those variables. We've got some multiplication going on here, some subtraction, but all that means is it's going to be a straight line when we graph it. It's going to be a linear function. All right, and then in the table here, so looking at this table, now I'm telling you, right, that it's a linear, this table is showing a linear function or a linear relationship. But looking at it, how do we know that this is a linear function? Well, first of all, we know it's a function because it meets the definition of a function, right? Each input has exactly one output, so that's taken care of. But also, if we look at the x values and the y values, we see that it has a constant rate of change. So if we were to compare the change in y to the change in x, I'm going to use this little triangle symbol here to represent change. So that triangle y, that I'm just using that as shorthand for change in y, and then change in x. So if we look at this table and we determine the change in y compared to change in x, we're going to see that it's the same always. It never changes. So what do I mean? Well, let's take a look at the change that happens when we move from 0 to 1. So how much are we increasing or decreasing by when we do that? When we go from 0 to 1, we're increasing by 1. So in that instance, the change that's happening in x would be 1. Now what about when we go from 1 to 2 in the y column? So when we went from 0 to 1 in the x column, we went from 1 to 2 in the y column. And that also was an increase of 1. So our change in y was 1. Now what happens when you simplify 1 to 1 or 1 over 1? Well, any number divided by itself is just 1. Okay, So let's try that again. Let's try that with looking at a different set of changes. So let's say I want to look at the change going from this set of xy to this last set of xy here. So in this case, I went from 1 to 3. That was a change of 2. Right? Going from 1 to 3 is a change of 2. And if I go from 2 to 4, so focusing on the same pairs of numbers, I have a change of 2, so an increase of 2. So in this case, my change in y was 2. My change in x was 2. Now what happens when I simplify 2 to 2, or 2 over 2? Well, if we divide the top and the bottom by the same numbers, so we can divide the top and the bottom by 2 here, we get 1 to 1. So we already see that this ratio has reduced to the same thing we had before, that 1 to 1. And we can simplify even further by just making this into a 1. So you should find, if you're looking at a table that has that's showing a linear relationship, you should find that no matter which XY pairs you use to determine the change should always simplify to the same thing. So in this case, we looked at a couple different sets of XY pairs, of coordinate pairs, but in both cases, they simplified to the same rate of change, this change of 1 to 1. And so that's how we know that this is a linear function, linear relationship. And again, we're going to see more examples of this later on. So yeah, more practice, I promise. All right, and then looking at this graph on the left-hand side. So looking at this graph, how do I know that this is showing a linear function? Well, it's a straight line. That's how I know it's linear. That's all there is to it. All right, now let's look at the right-hand side. So each of these representations on the right-hand side are showing a non-linear relationship. Non-linear relationship. So let's look at the first equation. Change colors here. So this first equation, y equals x to the power of 2, or y equals x squared. So based on what we talked about in the last slide here, based on that information, looking at this equation, this first equation, y equals x squared, how do we know that this is a non-linear function? Well, it's because of this exponent here. So there's an exponent on our input variable, which means this is a nonlinear function. If you were to graph this function, you would see that it would make a curved shape, kind of like this, so not a straight line. All right, what about this second equation here? So y equals 3 over x. How do we know that this is nonlinear? Well, we know it's nonlinear because our input variable is in the denominator of a fraction. So again, if we were to make this into a graph, this would not be a straight line. It would not be a straight line that passes the vertical line test. So we wouldn't be able to call it a linear function. So this is a non-linear function here. All right, and what about this table here? So we're gonna return to this idea of constant rate of change, constant rate of change. So let's look first at the first two XY pairs. So going from the first X value to the second X value, I see there's a change of 1. Okay. So if I'm keeping track of it down here, got my change in Y compared to my change in X. And by the way, the reason I'm using these little triangles is oftentimes in math, these little triangles are used to indicate change in something. They're not actually little triangles. What they are Greek lettered deltas. So not really something you need to remember, but just so you know why I'm writing it that way. So change in Y compared to change in X. So in that first set of values, the change in X was 1. Okay, and then the change in y going from 1 to 2, that's a change, that's an increase of 1. So my change in y was 1, and when I simplify that, it simplifies to 1. Okay, now let's compare the next set. So going from 1 to 2, again, that's a change in x of 1. And then going from 2 to 5, that's a change in y of 3. So the change in y was 3. So now I've got this ratio of 3 to 1. If I simplify it, I get 3. And that's different, right? So instead of, like in this blue table here, where no matter which pairs of x, y we decided to compare, we saw that the change in y compared to the change in x always reduced to 1, always reduced to the same thing. Doesn't have to be 1, but in that case it went to 1. Here we're getting different rates of change. So the rate of change is depending on like which x value you're using the function. The rate of change is non-constant, it's changing. So that's another reason we know that this is nonlinear. If you were to plot these values on a graph, you would find that they were not forming a straight line. You would find that they were making a curve on the graph. Okay, and then finally looking at this graph here, how do we know that this is nonlinear? Well, it's not a straight line. It's curved, so it's nonlinear. All right. So we're going to dig a little bit deeper into this idea of rate of change or slope. So we talk about slope when we're talking about a linear relationship between an input variable and an output variable, so typically between x and y. And what slope is it's the ratio, so it's the comparison of the change that's happening in y values compared to change in what's happening with the x values. So again, what we saw on the last slide, right? Change in y compared to change in x. And now there's several different ways that we can determine slope, or that we may be asked to determine slope. So we can determine slope by examining a graph. So if we're given a graph with a line on it, we may be able to just visually inspect the graph and figure out the slope. We'll see an example of that later. We can do it by looking at the table of values. So we actually did that on the last slide here with the blue table. We determined that the rate of change, that the slope for this table, for this relationship was 1, or 1 to 1. We can determine slope using 2 coordinate pairs, so 2 points, 2 xy pairs. And we can do that using the formula for calculating slope, and that formula is on the formula sheet. If you get out your formula sheet, if you look at the bottom half in the algebra section, you will see that there is a formula for slope. Slope of a line is what it'll say, right? Because slope is all about linear functions. And it'll say M. M is just a stand-in for slope, just a thing that we use. We use the letter M as shorthand for slope sometimes. So on your formula sheet, you will see that it says M equals y2 minus y1. And so that goes back to what we were talking about in terms of change, right? So we were talking about change in y. Well, how do you calculate change? You do it by subtracting. So this is saying subtract your 2 y values over x2 minus x1. So that's telling you to subtract your 2 x values. So this formula isn't really telling us anything we didn't already talk about. It's telling us to determine the change in y compared to the change in x. So if we're given 2 points or 2 coordinate pairs, that's the most straightforward way of calculating slope. And then finally, you can determine slope by looking at a linear equation. So most often we will encounter linear equations that are in one of these two forms. So this here, this is on your GED math formula sheet. This is called slope-intercept form of a line. We're not going to go into too much detail about that today. We're not going to talk too much about y-intercepts, but we are going to talk about slope. So in slope-intercept form, the slope is right here. So it is always the number that's being multiplied with the x, or with the input variable. So this is saying y equals some number times x plus some other number. So y equals the slope times x plus some other number. So we would, if we were looking at an equation that looks kind of like this, we would find the slope right here where the m is. And then very similarly with this second form of an equation, of a linear equation. So this form is what you'll see when we're talking about proportional relationships, which are a special type of linear relationship. In this case, you often see the letter K used instead of M. Again, that's just a placeholder for a number. There's no special reason why we use those letters. So here, K is just some number that's being multiplied with X. That's going to be our slope, or our rate of change. So whether or not we call it M or K or J or whatever it is, the slope, or the rate of change, is always going to be the number that's getting multiplied with X, or with the input variable. So if I have an equation that looks like this, y equals 1.5x minus 2. Well, I know that this 1.5, it's the number that's being multiplied with my input variable. So this is going to be my slope. It's my rate of change. What this is telling me is it's telling me every time my x increases by 1, my y is going to increase by 1.5, or 1.5. Okay, so let's take a look at an example here. So this is an example of a linear function and how we would determine the slope of this linear function. So first off, I start here with just a description of the linear function. So Darren pays $20 to rent a moving truck for the day, plus 50 cents per mile. So the total amount that Darren's gonna have to pay is gonna depend on the number of miles that he drives. And I just remember I made a mistake in this slide that I forgot to fix. So I'm gonna fix that while we chat. So right, the amount that Darren is gonna have to pay at the end of the day is gonna depend on the number of miles that he drives. So our input variable, or our independent variable, is gonna be the number of miles, right? Because it's 50 cents per mile. The bill is gonna depend on the number of miles. And then his total bill, the total amount he has to pay, will be the dependent variable, the output variable. So we have this relationship here between number of miles that he drives and the total amount that he has to pay. So I can also represent that using an equation. I've got that equation right here. So what this equation is telling me, if I wanted to calculate the total amount that Darren has to pay, well, I would say that the total amount that he needs to pay, total dollars, is going to be equal to 50 cents, right? 50 cents per mile. I just wrote it as 0.5, but we know that that's the same thing as 0.50. So 50 cents per mile times the number of miles. So X is the number of miles plus $20, right? Because he has to pay $20 no matter what. That's like the rental fee. So his total bill is going to be 50 cents per mile times the number of miles plus the $20 rental fee. And that's what this equation is showing us here. Okay, so let's return to this idea of slope before we get to the table or the graph. So if I was trying to identify the slope of this linear function, well, I think it's easiest to do that looking at the equation, right? We look at the equation, we're just looking for that number that's getting multiplied with the x, and that's right here. So the slope of this relationship is 0.5. Another way of saying that is the slope of this particular relationship is 50 cents per mile. 50 cents per mile. So each time I increase by 1 mile, so each time my x increases by 1, I'm going to see that my bill jumps up by 50 cents, right? So go up 1 mile, go up by 50 cents, go up 1 mile, go up by 50 cents. So the slope of my relationship is 0.5 or 50 cents per mile to be a little bit more specific. Now, if we look at the table, this is where I made a little mistake with my labeling. So our x variable is actually miles, not hours. I'm gonna have to remember to go back and change this. Okay, so here our x, right, is the number of miles we drive, and our y, our output, is the amount of dollars we have to pay, or that Darren has to pay to rent this truck. So if we drive 0 miles, we're still gonna have to pay $20 because it's $20 to rent the truck for the day, right? So even if we drive 0 miles, we're still paying $20. If I drive 1 mile, well, that's gonna add 50 cents onto my bill, right? So it'll be $20.50. If I drive 2 miles, that'll be another 50 cents. So now I'm up to $21. If I drive 3 miles, an extra 50 cents will be $21.50. If I drive 4 miles, add on another 50 cents, so now I'm up to $22, right? So this is just some examples of number of miles that Darren might drive and then what his bill is going to look like at the end of the day for the truck. So looking at this table, how could we determine the slope of this linear function? We were asked to determine the slope. Well, what we do is we look at the change in the y compared to the change in the x. So let's look at my first two xy pairs here. So here, going from 20 to 20.5, what's the change that happens there? How much do we increase by? Well, we're increasing by 0.5. So the change that just happened in the y direction was 0.5. Okay, now what about the change in x? We're going from 0 to 1, that's a change of 1. So our change in x was 1. 0.5 over 1, if we simplify that, we're going to get 0.5, right? Any number divided by 1 is itself. So simplifies to 0.5. You can really keep it in either form. You could keep it as 0.5 over 1. It's the same thing. Or you could write it as a fraction, right? We know that the decimal 0.5 is equivalent to 1/2. That's another perfectly correct way of expressing the slope in this situation. Now, just to be absolutely sure that we're dealing with a linear function here, that we're dealing with a constant rate of change, let's pick another set of xy pairs to double check the slope. So let's say I'm going from 20.5 to 21. So that's an increase of 0.5 or 1/2. And then in the x values went from 1 to 2. So again, that is an increase of 1. So we get the same thing, right? Our change in y was 0.5 and our change in x was 1, which would simplify to 0.5. What if we pick values that aren't right next to each other? So let's say we compare 20 to 22, so the first and last XY pairs. So going from 20 to 22 is an increase of 2. So I would write my change in Y as 2. And then going from first X value to the last X value, going from 0 to 4, is a change of 4, an increase of 4. So I've got 2 to 4. Now this ratio, we can divide the top and the bottom by 2. It'll simplify to 1 to 2, which is what we had before, right? We said how our rate of change, it could be written as 0.5 or 1/2. So doing it this way, we came up with 1/2 first, but we could write that as a decimal, right? If we do 1 divided by 2, we will get 0.5. So if you have a constant rate of change, that means no matter which XY pairs you choose, when you calculate change in Y to change in X, you should always come up with the same rate of change. That's what constant rate of change means. It's constant. It's always the same. Okay, so looking at the table, we determined again that the slope was 0.5 or 50 cents per mile. Now, we can also do that with graphs by looking at them visually. With this graph, which also has a mistake in it, so this graph says hours on it, it should say miles. So with this graph, it's going to be a little bit difficult just because we don't have the decimal values labeled on here. It's going to be a little bit difficult. But I can see that this table corresponds to this graph, right? So when if Darren goes 0 miles, he's going to have to pay $20. So when my X value is 0, right, when my X value is 0, my Y value is 20. That's this point right here, which lies along the line. If Darren drives 1 mile, he's going to have to pay $20.50. So just a little bit more than 20. He drives 2 miles, it's going to be $21. 3 miles, $21.50. 4 miles, 22, and so on. So it's going to be a little bit difficult if we were just given this graph to look at the graph and figure out what the slope is, because we've got these sort of in-between values that aren't labeled on the y-axis. We could maybe estimate what the slope is, but we might not know for sure. So we're going to look at another example later where we see an instance of it being pretty straightforward to use the graph to find the slope. All right. So here we're going to get some practice with identifying the slope. So for these 4 different representations of linear functions, we want to identify the slope. So what I would do, if I were you, is I would pause the video here, and for each of these 4, I would try to calculate the slope, and then when you think you've got your answers all written down, resume the video, and I'm going to go through it now. All right, so number 1, we've got this table of values here, and we want to calculate the slope. So again, right, I know that slope is change in y compared to change in x. So I'm going to start calculating my changes in y to changes in x. All right, so when I go from -2 to -1, that's a change in my x values of 1, right? I have increased by 1. Going from -2 to -1 is an increase of 1. That is a change of +1 for my x's. And then going from -4 to -2, that is an increase of 2. So that's a change of positive 2 because I've increased by 2. I could simplify this, right? 2 over 1 gives me a slope of 2. So I'm going to say here my slope is 2, but just to be extra sure, I want to double check that my rate of change is constant. So going from -1 to 0, that's an increase of 1. Going from -2 to 0, that's an increase of 2. So again, we would get the same change in y and the same change in x. It would reduce to 2. Same thing again, 0 to 1 is an increase of 1, and 0 to 2 is an increase of 2. So it's a constant rate of change. The change in y compared to the change in x is always going to reduce to 2. All right, moving on to number 2 here. So in this problem, we are given 2 points, so 2 coordinate pairs. That means I've got 2 x values. So I'm going to call this x1. I'm going to call this x2. And 2 y values. So this will be y2. And I'm sorry, there'll be y1, not y2. And then this will be y2. Now, if you are unsure how I know that the first one's x and the second one is y, and you're unsure of what a coordinate pair is, that means you need to go back and you need to watch last week's lesson, because we talked about points, we talked about coordinate pairs, we talked about how to graph points, all that stuff. So make sure you go back and take a look at that if you're not sure what I'm talking about here. Okay. And when we're given 2 points, we know that we can use the formula for our formula sheet to calculate the slope of a line. So again, our formula, if you're looking at your formula sheet right now, says that the slope is equal to y2 minus y1 compared to x2 minus x1. Now, the order here that you subtract the numbers in doesn't actually matter. You should, if you're subtracting correctly, you should still come up with the same slope no matter the order you do it in. But we'll follow the order here just to be careful. So following the formula and the labels that I've given my numbers here, it says y2 minus y1. So my y2 is 1. My y1 is 6, so 1 minus 6. And then my x2 is -1 minus x1, which is 4. So again, what this formula is telling us to do is it's telling us to subtract our y's, subtract our x's. It's really the same thing we just did in problem number 1, right? Calculating change in y compared to change in x. All right, so 1 minus 6. 1 minus 6 is equal to -5. And -1 minus 4 is equal to -5. So with these 2 points, we calculate a slope of -5 over -5. We simplify that. So we could think of it as -5 divided by -5. We're going to get 1. So the line, the linear function that passes through these 2 points has a slope of 1. That means each time x goes up by 1, the y is going to go up by 1. Okay. Let's take a look at number 3 here. So number 3, we've got a graph. Now, we're going to visually inspect this graph to figure out the slope. This graph, it's going to be possible for us to do that because we can see that there's some easily identifiable whole number points on here. So we're not going to have to deal with any points that are like floating in between whole numbers here. I'm not going to have to guess at any decimal values. We've got some clearly identifiable whole number points. All right, sorry about that, guys. Fixing a little background voices there. All right, so we were talking about this graph. So with this graph, I've got some easily identifiable whole number points. I'm not having to guess at any decimal values or anything like that. So I'm going to go ahead and I'm going to use these green points that are already up there for me. So I've got a point here and a point here. So this first point, what are the coordinates of this first point? So the coordinates of this point would be 0, 1, because it's at 0 on the x-axis and 1 on the y-axis. What about the coordinates of this second point? So the coordinates of this second point would be 2, 3, because it's lined up with 2 on the x-axis and 3 on the y-axis. Okay, so how can we just visually inspect this graph to determine slope? Well, we pick 2 points on the line, and starting with the leftmost point, starting with the leftmost point and working our way over to the rightmost point, we determine the change in the horizontal direction, so the change in x, and the change in the vertical direction, the change in y. So to get from my leftmost point to my rightmost point, I would need to go over 2 spaces. So I have a change in x of 2, and I would need to go up 2 spaces. So a change in y of 2. So that gives me a slope of 2 over 2. Remember, change in y over change in x. And this simplifies to 1 over 1. You could simplify that even further. We would just have a slope of 1. So when we have a slope of 1, again, what that means is every time your x increases by 1, every time your x increases by 1, your y also increases by 1. So we decided to kind of take this bigger step here. We went over 2 and up 2, but you'll see that we will follow this line if we actually go 1 by 1. So if we go over 1, up 1, we get to the line, over 1, up 1, we get to the line, over 1, up 1, over 1, up 1, over 1, up 1. So we have that constant rate of change of over 1, up 1, or up 1, over 1, however you want to say it. Okay. And then finally here for number 4, I look at my equation. I see the number that's being multiplied with my input variable with my x is 4. That means the slope is 4. That's all there is to it. The slope is 4. That means each time your x goes up by 1, your y is going to go up by 4. Okay. So next we're going to talk about proportional relationships. So proportional relationships are just a specific type of linear function. And what's special about them is that they are a straight line that goes through the origin. So they're not just a straight line, they're a straight line that goes through the origin. So the line includes the point 0, 0. If you remember that definition of the origin from last time. And so these proportional relationships, their equations have the form the plane going overhead. Their equations have the form of y equals kx. Now k is a constant, which just means it's a number. It's some number specific to the equation. And it compares y to x. Another name for k, another name for this number that shows up in the equation is what we've already been talking about. So k is slope, the rate of change. And specifically when we're talking about proportional relationships, we can think of that slope as being the same thing as the unit rate or the constant of proportionality. So if you love really long names for stuff, you could call it the constant of proportionality. Okay, and then we ask ourselves, why do we care about proportional relationships? Well, again, we care about them because they show up on math tests. They definitely show up on the GED test. And also because they're super common. They show up all the time in everyday life. So if you're trying to compare your hourly wages to your total earnings, if you're trying to compare time you've spent driving to distance you've spent driving, there's all of these relationships in our lives that can be described as proportional. And so we're gonna see how to work with those relationships, how to describe them, how to represent them in multiple ways, how to identify this special characteristic of slope, rate of change, unit rate, constant of proportionality. So up in the top right here, I've got an example of a proportional relationship. So I'm looking at this graph. How do I know it's a proportional relationship? Well, it's a straight line and it goes through the origin. So that I know it must be a proportional relationship. Now looking at this line, can I determine the slope? Can I determine the unit rate, the constant of proportionality, the rate of change? Can I determine that value? Yes, I can. So I'll do it by finding a couple of points that are sitting nicely on the grid line. So they have nice whole number values. So this first one is at 0, 0. That's a nice clear point. And then I can also tell that this line is going through the grid lines right here. So it's sitting at this point 2, 3. So if I'm starting with the leftmost point and going to the rightmost point, well, to get there, I would need to go over 2. So my change in x would be 2. And my change in y would be 1, 2, 3. It would be 3. So my slope is 3 over 2. So that's kind of the fraction representation of it. If we wanted to, we could write that as a decimal. So 3 divided by 2 gives us 1.5. Now remember, what slope really means is that each time our x goes up by 1, our y is going to go up by 1.5. And we can actually see that on this graph here. So if instead of looking at this 0.23, if I focus on where x is 1, so where x is 1, I find the point on my line, that is right about here. And that does actually look like the point 1, 1.5. So that is lining up at about 1.5 on the y-axis. So that's another way that I can identify the slope, the rate of change, the unit rate, the constant of proportionality when looking at a graph of a proportional relationship. So I could do it by picking any 2 points and calculating change in y to change in x, or I can find the point where x is 1. So this point where x is 1 Right, x is 1 and y is 1.5. That's going to be my unit rate. And we're going to see some more examples like this later. Okay, let's look at an example of a proportional relationship. Now this example should be very familiar to you if you saw last week's class. We talked about Robin and her hourly wages quite a bit last week. So we've got this situation where Robin is earning $15 per hour. $15 per hour. So we can represent that with an equation. We can say that Robin's total earnings are going to be equal to the hourly wage of $15 per hour times the number of hours that she works. So total earnings equal $15 per hour times the number of hours that she works. So here, this 15, this is our slope. Because this is a proportional relationship, you could also call it a unit rate. We know that in this situation, this is giving us our unit rate, our hourly rate. So a unit rate is a comparison to 1. So when we say something like $15 per hour, right, we're saying $15 per 1 hour. That's what a unit rate is. It's a comparison to 1. So in this relationship, the slope, or the rate of change, or the unit rate, or the constant of proportionality, is $15 per hour, or we could just say 15. All right, and then looking at our table here, well, we can use the table to identify our slope or our constant of proportionality. So I could do that in 2 ways. First way I could do it in is the same way we've been doing it this whole lesson. So determining or calculating the change in y compared to the change in x. So I can see in this table here, each time my x increases by 1, each time the x increases by 1, the y increases by 15. So it's the same every time. Every time y goes up by 15, means x is going to go up by 1. So that's a change in y of 15 and a change in x of 1, right? So $15 per 1 hour, or $15 an hour. Now, because this is a proportional relationship, another way that we can identify the slope or the unit rate for this linear relationship is by, again, finding that coordinate pair where x is 1. Right? So in this xy pair, x is 1 and y is 15. That's another way that we can identify our slope or our unit rate for this proportional relationship. Now let's say you were just given this table and you were asked to say what kind of a function or what kind of a relationship this is. Let's go through all of the kinds of relationships we've learned about so far. So let's say you're just given this blue table here and you're asked what kind of a relationship is this? Well, based on what we know so far, we could say that this is a function because for each input, there is only one output. We could say that it's linear because the rate of change in y compared to change in x is constant. It's always the same. It's always 15 to 1. And then further, we know that this is a proportional relationship because it passes through the origin. It passes through the point 0, 0. Just a little recap there on the different types of relationships we've learned about so far. All right, and then finally, looking at this graph. So again, this is a graph of the relationship between the hours that Robin works and the amount of money that she earns. And it basically shows us the same information as the table, as the equation, and as the verbal description. So if Robin works 0 hours, she's going to make $0. If she works 1 hour, she's going to make $15. 2 hours, $30. 3 hours, 45. 4 hours, 60, right? And we can keep going up here. And then we stopped at 8 just because we ran out of room. Right, but we know that Robin could work more hours than that, and we could potentially make a graph that shows that. Okay, so let's say we were looking at this graph. First of all, how would we know it's a proportional relationship? Well, we know it's a proportional relationship because it's a straight line that goes through the origin. And now how would we identify the slope of this proportional relationship? How would we identify the unit rate, the constant of proportionality? Well, we could do it by observing the change in y compared to the change in x for between any 2 points on the line. So if let's say we pick this point here and this point over here, right? Any 2 points on the line. Well, starting with the leftmost point and going to the rightmost point, I would need to go over 1, 2, 3, 4 in the x direction. So my change in x would be 4. And I would need to go up 1, so that's 15, 30, 45, 60, right? Because each of these blocks here represents 15. So 15, 30, 45, 60. So I get this slope of 60 over 4. And that slope will reduce to, sorry, got a neighbor cat running around here distracting me. So the slope will reduce to 60 over 4. No, the slope is 60 over 4, which will reduce to, well, I can divide the top and the bottom by 4. So it'll reduce to 15 over 1, which will reduce further to 15, which is what we already found, right? Same situation, we should get the same slope. Now, we could have also gotten that by just looking at the point where x is 1. So this point here, x is 1 and y is 15. So our slope or our unit rate for this proportional relationship is going to be $15 per hour. All right, let's compare these two situations here. So on the left-hand side, we've got Robin, who is earning $45 in 3 hours. On the right-hand side, we've got Irma, who is earning $88 in 8 hours. Who has a higher rate of pay? Well, let's figure that out. So we can figure it out for Robin. We know it's $45 in 3 hours. So her hourly pay, the unit rate for the slope for this situation, $45 divided by 3 hours is going to give us $15 per hour, right? So we already knew Robin was making $15 per hour. $15 per hour, per 1 hour. What about Irma? Well, she's making $88 in 8 hours. $88 divided by 8 hours is $11 an hour. That's Irma's hourly pay. That's going to be the unit rate, so $11 per hour. Now let's write an equation that describes the situation for both of them. Well, for Robin, we've already seen this equation, right? Her total earnings are going to be equal to $15 an hour times the number of hours that she works. For Irma, Irma's total earnings are going to be equal to $11 an hour times the number of hours that she works. Now let's make some tables for these ladies. So for Robin, we got this table set up here. So if Robin works 0 hours, she'll make $0. She works 1 hour, 15. 2 hours, 30. 3 hours, 45. Now again, there's no particular reason why I chose 0, 1, 2, and 3. Just did it because those are nice, small, easy numbers to deal with. They show the pattern. You could really pick any X values you wanted to. Now Irma, she works 0 hours. She's going to make $0. 1 hour, she can make $11. 2 hours, $22. 3 hours, $33. Okay. And then let's take a look at graphs for these ladies. So for Robin, she works 0 hours, she can make $0. So I'm going to put a point at 0, 0. 1 hour, she's going to work $15. She's going to earn $15, not work $15. So I've got a point here at 1:15. We've already seen this graph, right? So 2 hours, 30, 3 hours, 45, 4 hours, 60, and so on. Now if I try very hard, I can draw an approximately straight line through these points. And I can see my proportional relationship between hours and dollars. Let's do the same thing for Irma. So, of course, we start with 0, 0 here. And then for Irma, if she works 1 hour, she's going to make $11. So that's this line here. It's a little bit fainter, but we can see it. 2 hours, it's going to be $22. 3 hours is going to be $33. Make sure I'm picking the right line here. 4 hours is going to be $44. 5 hours would be $55. I can squeeze that onto this graph. There we go. Okay, and again, I can connect these into a roughly straight line. There we go. And now you can see here, if you compare the blue graph to the red graph, you can see the blue graph is a little bit steeper, right? Because Robin is earning more money per hour, the amount that she earns is increasing at a faster rate, right? Her line is steeper. She's accumulating money faster than Irma is. So that's a visual way we could compare their earnings. If we compare the blue line and the red line, we see the blue line is steeper, which shows us that Robin is earning more money than Irma is. All right, now let's try some practice problems here. So it says, using the information in the graph and table below, determine who had the fastest average speed. So we got Gerald over here. Let's determine his average speed. So his miles per hour, his unit rate. So take a minute, look at the table, see if you can figure it out. So his change in Y here, if we look at it, each time the change in Y is 60. And the change in X each time is 1. Change in X is 1. So he's going 60 miles per hour. His unit rate, his unit rate is 60 miles per hour. Now you could also determine that just from the XY pair that has an X value of 1, right? So that's telling us 60 miles in 1 hour. Our unit rate for Gerald is 60 miles an hour. What about Teresa? Well, fastest way to do that is to look at your graph, identify the point where the X value is 1. So that would be this point right here, right? When Teresa's driven 1 hour, she's gone 50 miles. So we could say her average speed, her unit rate, is going to be 50 miles per hour as well. We could do that without only, we don't have to look at the 150 point. We could look at this point here compared to this point here. So if we start at this point, we would need to go over 1, 2. So that's a change in X of 2. And we would go up 50, 100. So we'd go up by 100. So we end up with this ratio of 100 to 2. We simplify that. It's going to simplify to 50 over 1 or 50. Right? So we get the same unit rate either way. So who had the fastest average speed? Gerald did. Gerald had the fastest average speed. All right, number 2, Abe and Bonnie are both saving up to go on a vacation. Each of them saves a certain amount of money each month. Looking at the equations below, who has a higher monthly rate of savings? Hint, the input variable is the number of months, and the output variable is the total savings in dollars. So let's look at Abe's savings. So this equation is saying Abe's savings are equal to $75 times the number of months that he's been saving. So here, 75 is his rate of savings, or his the amount of money that he's putting away each month, right? It's his unit rate, $75 per month. Now what about Bonnie? Well, Bonnie is saving $80 a month times the number of months that she's been working on it. So Bonnie's rate of savings, her unit rate, is $80 per month. So we would say that Bonnie has a higher rate of savings. She's putting away more dollars per month. All right, number 3, the graph below compares Daisha's lemonade stand earnings to Terrence's lemonade stand earnings. How many more sales per hour is Terrence, blue, making compared to Daisha, green? So we're comparing Terrence's sales per hour to Daisha's sales per hour. So we need to figure out what those are first. So let's look at the green line first. Let's look at Daisha's line first. So both of these are straight lines going through the origin. I know they're proportional relationships. So one way I can figure out their sales per hour, or their hourly rate, or their unit rate, is by looking at the point on the line where X is 1. So for Daisha, that's right here. This is the point 1, 2. That means Daisha is making 2 sales per hour. You could also do that by comparing points. So if I start at this point, and let's say I go up to this point here, well, I would need to go over 1, 2, 3. So my change in x would be 3. And I would need to go up 1, 2, 3, 4, 5, 6. I would need to go up 6. So I get 6 over 3, which will reduce to 2 over 1, or 2 sales per hour. Right? So we get the same rate, we get the same unit rate either way. Now let's do the same for Terrence. So Terrence is the blue line. If I look at the point where x equals 1, I can see that it is 1, 5. So that means that Terrence is making 5 sales per hour. So how many more sales is Terrence making per hour? Well, if we take 5 sales minus 2 sales, we find that Terrence is making 3 more sales per hour than Daisha is. So the answer here would be 3. All right, and our final practice problem here. We're almost to the end. I know this has been a long one. So number 4, Joe sews 12 masks in 3 hours. First, determine her hourly rate of mask making. Then, represent the relationship between number of hours, x, and total masks sewn, y, using an equation, table, and graph. So we have 4 tasks to accomplish here. Let's do the first one. So determine her hourly rate of mask making. So right, this is going to be our slope, or unit rate, or constant of proportionality, or rate of change. Any of those words will work here. So her unit rate, we want to figure out the number of masks per hour. So if she's doing 12 masks in 3 hours, 12 over 3 simplifies to 4 over 1, right? That's 4 masks per hour, and we'll just simplify that to 4. So she's making 4 masks per hour. All right, so we figured out her hourly rate. Next up, let's do an equation. So y is total masks sewn. That's going to be equal to her hourly rate of 4 masks per hour times the number of hours that she works. That's our equation. All right, let's draw a table here. So making a list of example x and y values. Start with the simplest one. So if Joe sews for 0 hours, she's not going to make any masks. If she sews for 1 hour, we're expecting her to make 4 masks. 2 hours would be 8 masks. 3 hours would be 12 masks. I'm going to stop there, but we could keep going. Notice for most of the examples today that we haven't worked with many negative values. That's just because in these situations where we're talking about like masks per hour, or miles per hour, or dollars per hour, in those like real world situations that we were looking at, negative numbers just don't really make sense, right? So it wouldn't make sense for us to talk about Joe sewing for -1 hour or making like -4 masks. That's just not really relevant here. So you can, of course, have negative numbers in your proportional relationships. You can have negative numbers in your functions. Negative numbers are totally okay. It's just in these particular examples that we have been working on, they didn't show up very much. Lucky you. All right, so we got one more thing to do here. We're going to make our graph. So again, because negative numbers just aren't very relevant in this situation, I am going to exclude them from my graph. I'm just going to include the positive parts of my x and y axis. So we've got X and we've got Y. And remember, our X represents the number of hours and Y represents the number of masks. Now on the GED, because it's a computer-based test and most of the questions are multiple choice, it's never going to be a situation where you need to draw your own graph. However, I think drawing your own graph yourself, getting a little bit of practice with that can really just help you feel more comfortable with the different parts of a graph. It can help you understand a little more quickly and with a little bit more depth what's going on when you look at a graph. So it's good practice. All right, and then I'm just going to use my table as a guide here. So my hours are starting at 0 and they're going up to 3. So in between there, I've got 1, 2. Notice that my intervals here are evenly spaced. So each time I go up by an hour, it's the same amount of space each time, roughly. And then for my masks, I start at 0 and I go up to 12. So just to make this easy on myself, I'm gonna go up to 12 and then make my labels here for 4 and 8. Notice again that my intervals are evenly spaced each time I go up by 4, and that is the same amount of space on my graph each time. Okay, and now I'm gonna put my points on my graph. So I've got a point at 0, 0. Got a point at 1, 4. Got a point at 2, 8. And 3, 12. So this is roughly a straight line. I'm gonna connect them. And there's my graph. All right, guys, so that is the end of our lesson for this week. Be sure to stop by my Zoom tutoring hours on Wednesday or Thursday of this week, either in the morning, afternoon, or evening. The schedule's up on the Google Classroom, so you know where to look. You can also always send me a remind message or an email. And you've got a problem of the day to work on from Monday. You'll have worksheet Wednesday on Wednesday, and you will have a problem of the day on Friday. I've also posted on the Google Classroom a bunch of links to extra videos with more examples and explanations for these topics we've covered today, in case you just want some extra practice or if you are feeling a little confused, you might want to check those out. All right, guys, I will talk to you all soon. I hope you have a great week.